Hello friends, myself Aradi Mahajan presenting my video on function of complex variable point residue by Laurent series. Expand the function in Laurent series and hence find its residue and singularity. First example, f of z is equals to z square into e raised to minus z square. To obtain its Laurent series, we know the result. We take the help of that result, standard result. E raised to x is equal to 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. Therefore, replacing x by minus z square, we get the value of e raised to minus z square as 1 plus x means here minus z square plus square of that term minus z square and its square divided by 2 factorial plus minus z square and its cube divided by 3 factorial and so on. And then simplifying it, we get the first term as 1, then the second one as minus z square, the third term as plus z raised to 4 by 2 factorial minus z raised to 6 by 3 factorial and so on. And therefore, multiplying it by z square, we get that f of z as z square into e raised to minus z square is equals to multiplying throughout by z square to this, if we call this equation 1, 1 minus z square plus z raised to 4 by 2 factorial minus z raised to 6 by 3 factorial and so on. Multiplying by z square inside the bracket, we get the first term as z square, next one as z raised to 4 plus z raised to 6 by 2 factorial minus z raised to 8 divided by 3 factorial and so on. Equation number 2. This is the required Laurent series. It is the Laurent series of that function. And then we check, is there any term of 1 upon z minus a? There is no any term of 1 upon z minus a, and therefore residue of that function at z is equals to 0 is 0, or no residue, as there is no any term of 1 upon z minus a. If we have that term, its coefficient is called as a residue of that function at z is equals to 0. Here, as no term of 1 upon z minus a, we get the residue as 0. Second example, obtain the Laurent series for the function f of z is equals to 1 minus cos z divided by z. And to obtain its Laurent series, we take the help of the standard series for cos of x. We know the result of cos x is equals to 1 minus x square by 2 factorial plus x raised to 4 by 4 factorial minus x raised to 6 by 6 factorial and so on. Terms alternately positive, negative. Then replacing x by z, we get cos z as 1 minus z square by 2 factorial plus z raised to 4 by 4 factorial minus z raised to 6 by 6 factorial and so on. Then subtracting that series from 1, therefore we get 1 minus cos z is equals to 1 minus this series 1 minus z square by 2 factorial plus z raised to 4 by 4 factorial minus z raised to 6 by 6 factorial and so on. Simplifying it, 1 get cancelled. We get the first term as z square by 2 factorial, the second one as minus z raised to 4 by 4 factorial plus z raised to 6 by 6 factorial, and therefore we get that 1 minus cos z whole divided by z, as dividing by z throughout, we get here 1 by z multiplied by this series z square by 2 factorial minus z raised to 4 by 4 factorial plus z raised to 6 by 6 factorial and so on. Multiplying by 1 by z inside the bracket, we get that term as first one is z divided by 2 factorial minus, here we get z raised to 3 divided by 4 factorial. Next one is plus z raised to 5 by 6 factorial and so on. This is the required Laurent series. It is Laurent series. At pole z is equals to 0, and then we check whether there is any term of 1 upon z minus a. No any term of 1 upon z minus a, and therefore a residue is 0. Residue of that function at z is equals to 0 is 0 here, or no residue to this function f of z is equals to 1 minus cos z upon z. Third example, obtain the Laurent series for the function f of z is equals to e raised to z square upon z cube. Once again, we take the help of the standard series of e raised to x as 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. Infinite series. And using this, we get the series for e raised to z square as, replacing x by z square, we get first term as 1, next one as z square, next z square and its square divided by 2 factorial plus z square and its cube divided by 3 factorial and so on. Then simplifying it, we get that term as 1 plus z square plus z raised to 4 by 2 factorial plus z raised to 6 by 3 factorial and so on. And then we get that f of z is equals to e raised to z square divided by z cube, multiplying by that series by 1 by z cube, we get 1 plus z square plus z raised to 4 by 2 factorial plus z raised to 6 by 3 factorial and so on. And therefore, we get, simplifying it, multiplying it by inside by 1 by z cube, we get that first term as 1 by z cube, next z square by z cube, we get 1 by z, then next it is z upon 2 factorial, next one is z raised to 3 divided by 3 factorial and so on. We call this equation 2, and this is the required Laurent series. It is Laurent series. And then we check there is any term of 1 upon z minus a. 1 upon z cube, next one is 1 by z. Yes, there is a term of 1 by z and its coefficient, therefore we get residue of function f at z is equals to 0. The coefficient of 1 by z is here 1. Therefore, the residue of that function by Laurent series is 1. It is the coefficient of that 1 upon z term. Here it is 1. And therefore, this is the required residue obtained by Laurent series. Fourth example, find Laurent series for the function f of z is equal to sin z divided by z square. And to obtain its Laurent series, we take the help of the standard series for sin of x. We know the sin series for sin x as x minus x cube by 3 factorial plus x raised to 5 by 5 factorial and so on. Terms once again alternately positive and negative. And it exists for odd terms of x only. Therefore, we get the series of sin z as, replacing x by z, we get first term as z, next minus z cube by 3 factorial plus z raised to 5 by 5 factorial and so on. We call this as equation 1. Then determining the value of sin z by z square, multiplying this series by 1 by z square, we get 1 by z square multiplied by z minus z cube by 3 factorial plus z raised to 5 by 5 factorial and so on. Multiplying it inside the bracket, we get z by z square means 1 by z as the first term. Next one is z divided by 3 factorial. Next one is z raised to 3 z raised to 3 divided by 5 factorial and so on. This is the Laurent series. It is the Laurent series. Of that function f of z. Then we check whether there is any term of 1 by z or 1 upon z minus a. Here the first term is 1 by z. Then its coefficient, and therefore we get the residue of that function f at pole z is equals to 0 as 1. The coefficient of that 1 upon z is 1, and that term 1 is called as a residue of that function about the pole z is equals to 0, and this is I have obtained using a Laurent series. In my next video, I will discuss how we can determine the residue, and then it's used to determine the value of a contour integral. Cauchy's residue theorem. If you like my video, please share it as well as subscribe to my channel to receive the notification of my new videos. For that, you have to press the bell icon. Thank you. Thanks for watching.